Well, hello and welcome to our review session today, all about factoring. So we're going to go over all the work that you did in Math 10C that involved factoring. And this idea, being able to factor, is very, very important in math. You'll be needing these factoring skills to solve problems for the next 2 years or even past that if you decide to continue with more math classes. So this is something that you want to be absolutely great at. So we're going to start with the idea of factoring involves breaking numbers down. And when I say breaking numbers down, typically we can use another word, which would be dividing numbers. You started your Math 10C course talking about prime numbers and composite numbers. So what was a prime number? By definition, it was a number that had exactly two factors. Okay, and what was a composite number? A composite number were numbers that had more than two factors. More than two factors. So I could give you an example of a prime number as being 2, because if I think of all the numbers that can divide into 2, there are only two numbers, a 1 and a 2. So the only factors of 2 are 1 and 2. How about if I take the number 7? What numbers can divide into 7? Only 1 and 7. How about 29? Even though it's a larger number, the only things that can divide into it are 1 and 29. So 1 and 2 are factors of 2, 1 and 7 are factors of 7, 1 and 29 are factors of 29. So these 2, 7, and 29 are called prime numbers because they only have two factors. So composite numbers have more than two factors. So I can do a number like 4. If I think all the numbers I can divide by 4 by, I could get 1 and 2 and 4. So that's more than two factors. That's why we call 4 a composite number. And then there's 12. I have 1, 2, 3, 4, 6, and 12. So 12 has 6 factors. So this becomes a composite number. Notice we have one very special number, the number 1. If you think about that, would you call it prime or composite? Hopefully you'll call it neither, because if you called it prime, it means it has two numbers it can be divided by. If you called it composite, then it has three numbers it can be divided by, but the only number that it can be divided by is 1. So it doesn't fall into any of those categories. So if ever asked that, your answer would be that the number 1 is neither prime nor composite. So it's kind of in its own little world. Okay, so this idea of the word factor, what we're doing is we're kind of breaking a 4 down into other numbers that can create 4, but they're smaller versions of it. And these are numbers that can create 12, but they're smaller versions of it. For example, a 3 times a 4 could give me 12. So if someone gave you 3 times 4, you can absolutely say that that still is 12. So these are smaller versions of what we were given. In math, we would love to have the easiest version of something possible, so the most reduced or the most simplified version. So we love to reduce and we love to factor. Just think about fractions even. If you were given the fraction 15 over 45, that's kind of tough to picture. But if you could reduce or simplify it, and how do we do that? By dividing it down by factors. You remember we studied greatest common factors. That would be the largest number that both the numerator and denominator could be divided by. In this case, it's actually 15. So if I were to divide both the top and the bottom by 15, I'll get my reduced version of this. So 15 divided by 15 is 1. 45 divided by 15 is a third. So these are mathematically or numerically the same number. But what would I rather deal with if I had a bunch of math to do? All day long, I would rather deal with 1 over 3 than this. They are the same. So if you pictured a pizza and you were talking about your portion of that pizza is 1/3, that's very easy to visualize. This is the same value, but now instead of having divided the pizza into 3 pieces, you've taken the same pizza and you've divided it into 45 pieces. That is the idea. So here you had 3 pieces. Here you have 45. So to eat the equivalent amount, this person would eat 1 huge slice. This person would have to eat 50 15 little ones, but at the end of the day, those amounts would be the same. So 15 out of 45 is the same as 1 over 3. But this is way preferable to be doing my math with. Just to visualize it. And again, in further math courses, maybe you're not going to be allowed to use a calculator, so everything's by hand. This is just way more efficient to have to deal with this one. So we now are going to talk about polynomials, right? So you did a unit on polynomials. So we better remember what polynomials are. We had monomials, binomials, trinomials. Usually there was a letter or a variable involved. Didn't have to be. And then that letter, that variable, could have an exponent on it. So all those things together are really the definition of what a polynomial is. If I said, is 5 a polynomial? It is. But you might say, well, there's no letter with it. Actually, I can write any letter next to it that I want. I could put an X, but the exponent will determine what this is really evaluated as. So anything to the power of 0 makes this entity equal 1. So what does this really say? If this is a 1, this says 5 times 1. So these really are the same. So can I call 5 a polynomial? Yes, you can, because you can always insert a letter there. If you wanted it to be M, that would be fine. So plain numbers are polynomials, but we don't deal with that a lot. We just deal with that. A 5 is a 5. So we're kind of more used to seeing, let's say, something like that. So this you would say is a monomial. It is degree 3. And what is very important for polynomials is when you look at the exponents on the variables. This is a variable. Okay, the 6 is not a variable. The 6 is a coefficient. This up here needs to be a whole number. So whatever my letter is, A, B, C, D, whatever, X, this has to be a whole number. And if it is, and this is a valid real number coefficient in front, then I have a polynomial. Now, what are whole numbers? We called that, the abbreviation was capital W, and we said they are the set of numbers that start at 0 and go forever and ever to eternity, but no fractions and no negatives. So as long as this exponent on the variable is one of these, I have a polynomial. So if I made one little change, if I did that, this is not a polynomial anymore because this -3 does not belong to the set of whole numbers. So this would be something else that you'll study later. So let's pretend this is a 3, and now I go, oh, plus 2x to the 4 minus 5. This is now a trinomial because it has 1, 2, 3 terms, and everything's good. All of the exponents on my variables are whole numbers. Because why? Here is a 1. Because why? Here is an x to the 0. This term would be called degree 5 because you add up all the exponents on the variables to get your degree. This term is degree 3. This term would be degree 0. So it's a trinomial. If somebody asked you what was the winning degree or what is the degree of this entire polynomial, you pick the term that had the highest value. So these totaled 5. So this trinomial would be degree 5. Okay? So we can have all sorts of stuff, but you have to make sure you have true numbers in front, not something that you couldn't figure out. Like if this said root of -5, that's not a real number. Your calculator would give you error. So if something doesn't exist in math, don't give it a name. Don't say this is a trinomial. It simply doesn't exist. So what we're trying to do, as we did a minute ago, we reduced a fraction. Now we would like to be able to reduce polynomials or simplify them in case within that polynomial, they have numbers that are bigger than they need to be. So here's an example of a trinomial. Let's say 10x squared minus 6x plus 2. Okay, so can this be simplified or reduced? So we talk about greatest common factors. So I'm going to look, this is a trinomial. It has 1, 2, 3 terms. I'm just going to focus on the number values first. So is there anything that 10 and -6 and 2 can all be divided by? Yep, they can all be divided by 2. So you can just do that in your head, but you mustn't forget this 2 is still part of our work. So if I'm simplifying this, I would say, okay, I took out a 2, and that 2 is going to sit out front. Now, this was a trinomial. you better be left with a trinomial after you're done reducing. However you want to do this, like I say, if you want to do it in your head, 10 divided by 2 would leave a 5. That's fine. If you want to actually show that you're dividing each of these by 2, you can do that as well. What is 10 divided by 2? 5. I did not take any x's out. This x squared really means there's 2 x's sitting here, but I didn't take out or divide out an x, so I'm still left with those 2 x's there. Negative 6 divided by 2 would leave me negative 3. And I didn't touch that x, and then I have a plus, so I keep my plus. 2 divided by 2 is a 1. But you didn't have to write these 2's. You could have just done that in your head. 10 divided by 2 left a 5. Negative 6 divided by 2 left a negative 3. 2 divided by a 2 left a 1. So notice I started with a trinomial, I finished with a trinomial, but I have it in a much nicer reduced form. And that can work with binomials as well. Let's say I had something like this. Okay, so now I have a binomial. For sure, when I'm done, I will also have a binomial. This is the first term, this is the second. Make sure, so these are my coefficients, so I would deal with them by looking for their GCF, greatest common factor. But make sure you know this a cubed means there's 3 a's and 2 b's. This means there's 1 a and 4 b's. So remember, I'm looking for what do they have in common, and then I'm going to take that out or divide that out. So first, my GCF for 24 and 15 would be a 3. So that's coming out. Then I look at the letters. Let's focus on the A's first. This has 3 A's, this has 1 A. So I can't say, oh, I'm going to take 3 A's out of this guy and 3 A's out of this guy. This one doesn't have 3 A's. So the most that they share in common is 1 A. So I can only take 1 A out of each of these. You can put a little one there if you want. This has 2 B's, this has 4 B's. So the most that can come out of both would be B squared. So that's called my GCF. That's what I'm taking out. This was a binomial. I'm still going to be left with a binomial, but they'll be smaller. They will be a reduced version here versus what I had here. So 24 divided by 3 leaves me an 8. I had 3 A's, but I took 1 out, which would leave me 2 A's. So I'm really subtracting these exponents as well. 3 minus 1 left me 2. I had 2 B's sitting here, but I took 2 B's out, so there's none left. I haven't played around and taken away other negative signs, so I'm keeping that plus. So 15 divided by 3 leaves me 5. I had 1 A, but I took it out, so there's no A's left now. I had 4 B's, but I took 2 out, so there's 2 B's now left. Your work is always so easy to check. If I wanted to check if this was correct, I could go through and multiply and see if I had my original trinomial, and I can always do a check here as well. Go back and multiply, see if I had my original trinomial. Okay, so what you really want to remember, start with a trinomial, you'll end with a trinomial. Start with a binomial, you'll end with a binomial. And what you should always do in any kind of factoring, always first step would be to see what they have in common, and you should always take that out first. Okay, so there's a booklet attached for factoring practice in your Google Classroom. So you probably want to stop this video right now and go try all the work in your booklet on page 52. Okay, so you could pause this and go do that. Then when you come back, we'll be looking at the next section, which is reminding ourselves what happened when we multiplied 2 binomials. Okay, so for example, let's say I multiplied x plus 4 times x minus 7. So the idea here is you can only do one thing at a time, okay? So I have 2 things here that eventually need to be multiplied to everything there. So you pretend one of them's not here for a minute, and you do one thing at a time. So because you're crossing a bracket, you know this means multiply. So x to the 1 times x to the 1 would give me x squared. So I've done that one. Now I go and do a negative 7 times an x, so negative 7x. If there was more things here, then I would do more arrows and more multiplying. But there isn't, so I'm done. So now it's time for the 4's turn. If this were a negative 4, I would continue with a negative 4. But it isn't. It's positive 4 times an x will be plus 4x. Positive 4 times a negative 7 would be negative 28. So you've done all possible multiplying you can. Always look for like terms. Those are terms whose variables are identical. That's next to the 1, and so is that. So if I add these together, my answer will be plain old x's, but there's negative 7 of them plus 4 of them. So putting those two together would give me negative 3x of them. So I had a binomial times a binomial, and very often that results in a trinomial. So the purpose of factoring is now somebody gives you this and says, where did it come from? Well, there's a big time connection. If you keep in your mind that a trinomial probably came from a binomial times a binomial, the firsts times the firsts here would have given you what your original value or your first value in your trinomial would have been. So if you think about that, these had to both be x's. The only way that I could go this times this and get an x squared is really if they were both x's. And then a bunch of other stuff happened. There were all sorts of arrows. But ultimately, these two together, so the first two together did give me this x squared. And then the very last two multiplications I did is where I got that negative 28. So because this was the focus of your unit and being really good factoring trinomials, we need to come up with a plan. So when we see a trinomial, or in this case something starting here with an even exponent like an x squared, there's a really good chance my first step should be starting off with, here's two brackets. I'm going to try and work backwards and see if I can figure out where this came from. Okay. Now we're going to start with the easiest ones of all. What if I gave you x plus 3 times x minus 3? And I go through that same procedure. I take this x to everything, and then I take the 3 to everything. I will get x squared minus 3x plus 3x minus 9. And something interesting happens here. These are exact opposites of each other, so they're going to cancel out. And in this case, when I'm done, I end up with a binomial, not a trinomial that I did here when I multiplied a binomial times a binomial. Interesting. Okay. How about if I do something else here? I'm going to go, it doesn't have to be m or x. We can go m minus 6, m plus 6. And again, doing one thing at a time, right? And all my multiplying, I will end up with m squared plus 6m minus 6m minus 36. Same thing happened. Exact opposites cancel, and I'm left with this. Okay, and I could even add more letters in here. How about 3x plus y and 3x minus y? So doing all that multiplying, 9x squared minus 3xy plus 3xy minus y squared. So when I did these two together, I wouldn't say y 3x. Look at that, y 3x. That just looks weird. In math, we like to have our number first, and then the rest of the letters we like to put in alphabetical order. So the number should come first, so the 3 should come first, and then it should be xy. That's why I wrote that one like that one. But it happened again. So I'm left with a binomial. So there's something very, very special about what happened. Why did we not end up with trinomials? Look at where they came from. They came from a bi times a bi that were almost identical except for their signs in the middle. And because they were pretty much identical, I had things resulting that looked almost the same but had opposite signs. So there's a very special name for these three things here. They are called a difference of squares. So to be a difference of squares, you need to be a binomial, you need to have a difference, or you need to have a minus sign, and I need to be able to figure out the square roots of each of these things. So the purpose of this unit, or factoring, is now you're given these, and your job is to go back and figure out where did they come from. Can you see the connection? Going backwards from here to here, or from here to here, or from here to here. Because if you can see the connection, then this type of factoring, when you see these binomials, actually becomes quite easy for you. Okay, so it's called a difference of squares. So to be, right, to be a difference of squares, there are 3 requirements. Number 1, you need to be a binomial. And some binomials can look pretty elaborate, but really we need to have 2 terms there, okay? So the idea is so you're going to be given a binomial, and when we factor it, it's going to come from something that looked like this. They almost are identical. This and this are the same, this and this are the same, but one of the brackets has a plus and one of them has a minus. Also, to recognize the difference of squares, you better see a subtract sign in it. And last of all, you have to know the square root, or be able to find the square root of each term. So going back to, no, let's do some other ones. So I give you x squared minus 49. Is this a difference of squares? Well, if it meets all 3 requirements, then yes, it is. Is this a binomial? Yes, it is. Is it a subtract sign in the middle? Yes, it is. And can I figure out the square root of x squared? Yep, it came from an x being squared. Can I figure out the square root of 49? Yep, that's a 7. So it met all 3 requirements. So this is easy. You give yourself 2 brackets, one's a plus and one's a minus. What needed to have started each bracket to have gotten x squared? You needed to have started with x's. What had to finish each bracket to end up with the 49? They each had to be 7s. And you can absolutely check this. You can multiply this out and you'll see in the interior there was a minus 7x and a plus 7x, and that's why they're not here. They're gone. Okay, another one. How about if I've got x squared plus 16? Is that a difference of squares? Well, is this a binomial? Yes, it is. Is it a subtract sign? No, it isn't. So do not try it. Maybe this can be factored, but definitely not into a situation like this. So forget about that one. And how about if I had this one, 2m squared minus 50, and someone says, is this a difference of squares? Well, is it a binomial? Yes, it is. Is it a subtract sign? Yes, it is. And do I know the square root of these? No, I don't. But remember what I said before. The first type of factoring you should always, always try is common factoring. Is there a GCF you can take out? Yeah, these can both be divided by 2. So if I divided both terms by 2, so I take out a 2. 2 divided by 2 would leave nothing except these m squareds. A negative 50 divided by 2 would leave a negative 25. So now I'm just focusing inside the brackets here, and I'm going to try this again. Could this be a difference of squares? Is it a binomial? Yes. Is it a subtract sign? Yes. Do I know the square root of each term? Yes, I do. So how could I simplify this even further? 2 brackets, one with a plus, one with a minus. The square root of the m squared started each term. The square root of the 25 ended each term, and then I'm done. Now, these can get much more difficult, so we'll do 2 more examples. How about this one? Okay, binomial, yes. Subtract sign, yes. Do I know the square roots? Yes. So this comes from 2 brackets. They look identical. Square root of this started each bracket. So the square root of 16 is 4. The square root of t to the 4 is t squared. The square root of 1 is 1. So for a minute I think I'm done, but being ever observant, there's another difference of squares. It meets all 3 requirements. It's a binomial, it has a minus sign, and I can keep going. I can figure out the square roots of each of these. So this is done. I can't go any further with this one because it's not a difference. It's a plus sign. But this one could be broken down again. So the square root of 4t squared would be 2t. So they each start with 2t. The square root of 1 is 1. One of these has a plus, one of them has a minus. Now I'm done. I can't go any further. That's not a difference. That's not a difference. This is, but I don't know the square root of this, so I would be done. Okay, and our last one here, let's really take it as tough as we can get. How about this? Okay, so if I'm looking at this one now, does it meet the three requirements? It is a binomial, it is a minus, and I do know the square root of this, and you actually do know the square root of m to the 6. Not the square root of 6, but the square root of m to the 6, you do know. You do know the square root of this, and you do know the square root of n to the 10. Not 10, but n to the 10. So if we think of, if I asked you what's the square root of 9, you'd say 3, and you're right. How come? Because 3 times 3 is 9, right? In other words, we can say the square root of 9 is 3. So think about square roots. These needed to be the same, and when you multiply them together, you got the value you were given. So let's focus and think about this. What two things times together, and they have to be the same, would give me m to the 6? Well, m to the 3 times m to the 3 would give me m to the 6, because that's our exponent stuff. So a 3 plus a 3 would give me 6. So then I know the square root of m to the 6. It must be m to the 3. Not because 3 is the square root of 6, because it takes 2 of these times together to give me this, just like it took 2 of these times together to give me this. So this meets all the requirements, so I can factor it now. 1 is a plus, 1's a minus. Square root is 9. Square root of 9 is the 3, so we have 3's. Square root of m to the 6 would be m to the 3. Square root of 64 is 8. Square root of n to the 10. Think about it. What two things, when they times together, and they had to be equal, would give you n to the 10? Must be n to the 5. So it looks like I'm done. This could be maybe another difference of squares because there's a minus, but anything with an odd exponent on it, I can't figure out a nice value of its square root or where it came from. So I would be done. Okay, so now you want to practice difference of squares. So you can stop the video and you can go and do page 53 in that handout. So we've made it past the easy stuff. So like I said, you can pause and then come back, and then you would continue your study with trinomials. Okay, 2 types of trinomials in math. And they're typically given kind of this skeleton look. Okay, you're told here's a trinomial. We call it ax squared plus bx plus c. The a and the b and the c are simply numbers. The most important thing in terms of you to consider when factoring is, what is this a value? There's 2 choices. A can be a 1, and that's when you have very easy factoring. But if the a is not a 1, this becomes much more difficult factoring, and you would do a totally different procedure with it. We've seen before today, when we took 2 binomials and did all that multiplying, we typically got a trinomial. So remember that. Also remember, the first thing you should ever try is to common factor. So the first scenario we're going to look at is when we have this trinomial and my a is a 0. So just as long as you understand this a, b, and c. Okay, so let's say I had x squared plus 4x minus 12. A is what's in front of here, a is what's in front of the x squared, b is what's in front of the x, and c is your constant term. So what's in front of my x squared? A 1. So I would say a is 1. What's in front of my x? A positive 4. So b would be positive 4. What is the term all by itself, or the constant term? That's a negative 12. So in this trinomial, a is a 1, b is a 4, c is a negative 12. That's all that means. If someone asked me to factor this, the first thing, always, you should check out, does the x squared have a 1 or not? If the x squared has a 1, okay, then this is a very easy process. You start here, then you jump to the end, and then you think about the middle. So because this is a 1, this is an easy question to do. I know there's a really good chance that this thing came from 2 binomials. What had to go here and here so that when we multiply them, we got x squared? Not very many choices in this case. They had to both be x's. If this were m squared, these would both be m's. Then this is where you look second. And you start in your head with your times tables. We know this times this gave me negative 12. Is there only one way to get negative 12? No, there's lots of ways to get 12. Actually, don't even worry about the negative. So off to the side, you might actually want to write them down. What are all my factors or different ways I could have gotten 12? A 1 and a 12, right? 1 times 12 could have given me 12, so there could have been a 1 here and a 12 here, or maybe a 2 and a 6, or maybe a 3 and a 4. So one of these is going to work. Maybe a 1 here and a 12 here, or a 2 here and a 6 here, or a 3 here and a 4 here. How do you decide? That's now when you look at the middle, okay? You're aiming for a 4. This is going to tell you which magic pair here, or which pair here is the magic set. Is there any way, either by putting a plus or a minus in between these and giving them different signs, is there any way you could put a 1 and a 12 together by adding or subtracting and get a 4? Nope. So those aren't my answers. Is there any way you could put a 2 and a 6 together and get a 4? Yes, you could. If the 2's were negative and the 6's were positive and you added them together, that's exactly what you get. So I don't even need to look further. These are my answers. One of the brackets has a -2 and one of the brackets has a +6. And it doesn't matter. I could have had the +6 here and the -2 here. It would be so easy to check. I could now do my arrows and go back and multiply, and I would see, yes, this is now the factored form of the trinomial that I was given. So this is the expanded form, this would be the reduced or the factored form, and this will be a very beneficial thing here for you to figure out. Okay, let's do another one. Again, this is just review. You've done lots of these. Let's say I've got this now. Okay, so remember, step 1, is this going to be an easy or not easy question? It's going to be easy because the front A value is a 1. So now that we know it's easy, these each started with an M. Now, step 2, this is where you always look second. 24. So you start with your times tables. Well, I can do that. I can get 24 by 1 times 24, 2 times 12, 3 times 8, 4 times 6. Which one is it? Well, this will decide it for you. You look through these two. Any way they could ever add or subtract and give you 11? Nope. Gone. These two, any way could you add or subtract them together and get 11? Nope. They're gone. A 3 and an 8? Yes. A -3 plus a -8 would give you -11. There's your magic numbers, -3, -8. And you can check and you'd be done. Okay, so let's do another one here. How about 5d cubed plus 4d squared plus 80d? It's a trinomial, and I'm looking at this thing, and the first thing I'm supposed to do is see if the front number's a 1, but it isn't. So this might not be such an easy question unless I can take out a greatest common factor. So looking at the numbers first, anything that 5, 40, and 80 have in common, yeah, they can all be divided by 5. So I'm going to divide them all by 5, and then look at the letter parts. This has 3 D's, this has 2, this has 1, so I can also take out, or common factor out, a D. So here's what's coming out. 5D from all of these. A 5D from here would leave D squared. A 5 divided out of a 40 would leave me 8. A D squared, take out 1D, would still leave a D. 80 divided by 5 is 16, and then I'm done. Okay, so now here's the trinomial. This front stuff is just the GCF. So is this one of our nice trinomials? Is the A value right here a 1? Yes, it is. So this will be quite easy to continue with. Don't forget to write the 5D. So now we're going to say this starts with a D and this starts with a D. Now here come my times tables. How can I get 16, 1 and 16, 2 and 8, or 4 and 4? The 8 will tell you which of these is the right set. So a 4 and a 4 is the correct set. They're both plus. So plus 4 and plus 4. And you might want to write this a little bit shorter. So I can just, for ease, change this to 4 plus D and put a squared on it. telling everybody I actually have 2 of these d plus 4s. Okay, so that's the nice, easy type of factoring. Can they make this a little tougher by throwing some other things at you? Sure. How about if it looks like this? Something like this should strike you as a little bit odd. It's not in what we call descending order. We focus on our letters, and we want to start with the letter with the highest exponent on it. And this is backwards, right? I would rather this be the other way, but that's okay. If it is written backwards, this is the C, this is the B, and this would be the A. So my A is actually a -1. In this case, that's okay. As long as this is some kind of a 1, I can do my brackets, and I can figure out, well, what must have been at the end of each bracket here to end up with a y squared? This must be y. So these two together gave me 14. So here I go again. How could I have gotten 14? Not too many choices, right? A 1 and a 14 or a 2 and a 7. Remember, we're aiming to get a 5, so this is the magic pair. To get a positive 5, you need the 2's to be negative and the 7's to be positive. So how are you going to do that to make the 2's negative and the 7's positive? So this thing is going to look good. We need a number here and a number here. So if I want the 7's to be positive and the 2's to be negative, the idea is 2 things together here and 2 things together here. One of them needs to be a positive 7, one needs to be a -2. So you play around with this. I could have either one in either bracket, but this is how it's going to have to look. A little bit confusing, but if you do your checks, this 2 times this y will create a -2y. This 7 times this y will create a positive 7. And that's what we were going for. But it's really important to check your work if this thing wasn't in the right order. Could you have turned it around so it was in the right order? Yes. You would have said minus y squared plus 5y plus 14. But now you need this a to be a positive 1. So your first step would be to common factor out a -1 from everything. So that would create this first term, or change this first term to y squared. The next one would be -5y, and the next one would be -7. So now we're kind of back to normal. We see we have a 1, so I would keep this negative, which is a -1 sitting here, and do as we did before, right? Oops, sorry, this was a 14, not a 7. And I'd go off to the side with my ways of getting 14. This one will work, and I know that the 2's need to be positive, the 7's need to be negative, and maybe that's an easier way for you to do it, but you wouldn't want to forget having that -1 out front. But this and this are identical. It's kind of just depending how you want to go through and look at things, okay? So, probably time to stop the video again and practice this type of trinomial where the a value is a 1. So you're going to go to your booklet and you're going to work through pages 58 to 60. Okay, and then you'll be really good at the basic type of trinomials. Okay, so then when you're done that, you're going to come back to this video, which is about at 38 minutes already. And we're going to look at, all right, let's keep going with the trinomials, but now we're going to look at the type of trinomial where that first value, that a, is not a 1. Now this is much more difficult, or more work, more things to consider when this first value is not a 1. But always you would try, maybe you could get rid of this by factoring out a number, because it's worth trying that first to ease up your work. So if it's not a 1, there are all sorts of different ways that we can teach how to factor this. One thing is called decomposition. It's not really taught very much anymore, but if you're Googling or looking up things, you might see this decomposition method. If you like it, you can use it. There's nothing wrong with it. Guess and checking is probably the best in terms of down the road. Being able to very quickly look through something, but it takes really good multiplication skills and doing some work in your head. Then there's another method called kind of inspection or making crosses method or Chinese method. So as I'm going through these next few examples, I'm going to do that method. I'm going to show you guess and check because it is the best one, but it takes a little bit more practice and doing a little bit more in your head, but mostly focusing on this inspection method. So here's an example. I'll give you this trinomial. And again, where you would always start is looking at the front number with the A. That is not a 1. So don't even draw 2 brackets and think you're going to do something there unless you're using a guess and check method. So guess and check would be you realizing, because this is squared, it came from 2 binomials. And this times this gave you 3x squared. Well, since 3 is prime, there aren't very many options. One of these needed to be have a 3x, and the other needed to have an x. There's no other way that this times this could have ever given me 3x squared. And then I look here. These two together are going to have to give me a 7. So maybe this is a 1 and maybe this is a 7. So why don't I just try this? Why don't I just do the multiplying and see if this works and gives me, when I add the middle terms together, see if I get a 4. So this times this would have been 3x squared. But this outer loop, 3x times x would have been 21x. And this inner loop, timesing these two together, would have given me a 1x. Remember, I'm going for the middle. Would a 1 and a 21 ever add and give me a 4? No. So that tells me this choice was wrong. They probably need to be swapped. So I'm going to try this instead. Still 3x and x, but I'm going to swap, put the 7 here and the 1 here. Outside loop, inside loop. That times that is 3x. This times this is 7x. Is there any way these could go together and give me a 4? Yes, if the 7s were positive and the 3s were negative. So the 7s need to be positive, the 3s need to be negative. So we have now factored this trinomial into those 2 binomials. That would be by guessing and checking, or loops or something. And this was very easy because 3 and 7 were prime. I didn't have a whole bunch of options of what could have gone here. If this last number had been 100, oh my goodness, 1 and 100 or 2 and 50 or 4 and 25 or 5 and 20 or 50, like, oh, not quite so easy. So I'm going to do the same question using what's called the inspection or Chinese method. So kind of how you would set it up. Okay, you are just going to give yourself some little boxes underneath the first and the last term, and you're going to pick 2 numbers that do multiply and give you this first value. So I'm going to go 1 and 3. So a 1 and a 3 would give me a 3. How could I get a 7? Let's say I do a 7 and a 1. Now you do these crosses. This 4 still is going to become very important. And the reason you did this, of course, is because the first number wasn't a 1. So you make a cross and you times, and the crosses always have to end with the tip at the top. From wherever you're going, you're making a cross. So if I end up at the top, I write my product at the top. So 3 times 7 is 21. This way, I get a 1. So I'm going to put these together, and remember what I'm trying to get. I'm trying to get a 4. Well, a 21 and a 1 will never, and I should use pencil if I were actually doing this because I'd want to erase if something didn't work. But a 21 and 1 will never give me a 4. So change the order. Make this the 1 and make this the 7. These two are still factors of 7. So now 3 times 1 is a 3. 1 times 7 is a 7. Is there any way these could go together and give me a 4? Yes. If the 3s were negative and the 7s were positive, I would get positive 4. So here's what you do. Since the top number had the negative, you transfer a negative or a minus sign right here. Because this bottom was a plus, you transfer a plus to right here. These 2 values were created, and when we times them, we got a 3x squared. So each of these actually have an x with them. So it does start to look messy, but you know what this top thing says? It says 1x minus 1. So it says 1x minus 1. This says 3x plus 7. 3x plus 7. Exactly the same thing that we got here. All right. So this worked quite quickly and easily because we had very small, or we had prime numbers here. As soon as they're not prime, you might really need to be doing a lot of erasing and a lot of trying different combinations of things. So here's an example of one that might take a little bit more work. 12m squared minus 8m minus 15. So first thing, not a 1, but can I take that 12 out from everything? No. So this is a tougher question. I could set up brackets and do a guess and check. So I could say, well, how could I maybe have gotten a 12? Maybe a 3m and a 4m. How could I get 15? Maybe a 5 and a 3. And then I would do these loops. And always I'm going for the middle. So the outside loop is 15. The inside loop is 12. No, this is wrong. A 15 and a 12 won't give me 8. So then maybe swap these. Maybe do a 5 and a 3. This is 9. This is 20. That doesn't work either. So maybe that's not how I get 15. Maybe I should get 15 by doing a 1 and a 15. So now I would try that. And if that didn't work, swap the 15s, etc., etc. So, and then if all that fails, then you'd say, here's probably where I made the goof. Maybe the 12 didn't come from a 3 and a 4. Maybe it came from a 2 and a 6. So this can take a long time. So be prepared to have lots of paper and try different things. So whether you're going to do a guess and a check or an inspection, which they're really the same thing, be prepared for lots of trial and error. So if I want to do this one using that inspection or Chinese method, I'm going to give myself boxes here and I'm going to grab a pencil. Say, okay, here I was trying 3 and 4s. I'm going to try a 2 and a 6. Okay. So how am I going to get a 15 over here? I don't know. Let's try 5 and 3. So when I multiply this way, I get 30. Hope you can see that. I want to use pencil because I might have to erase. And when I multiply this way, I get 6. So remember what I'm trying to get. I'm trying to get 8. Will 30 and a 6 give me 8? Nope. So I'm going to switch this 5 and this 3. I'll put the 3 on top and the 5 on the bottom. So if I do that, so 6 times 3 is 18, 2 times 5 is 10. That would work. I can get a negative 8 if I make these 18s negative and these 10s positive. So that's what I do. I grab this minus and I put it here. I grab this plus and I put it here. These were in the m squared column. So this has an m and this has an m. So there's one of my factors, there's the other factor. So I have 2m minus 3 and 6m plus 5. That is the proper factored form of that trinomial right there. So does it take more time? Yes, it does. Okay, so there could be lots. Always watch out, look for a common factor. Always take a common factor out first. If everything here had m's, then maybe my first step should have been to take out a whole bunch of m's. And be aware, sometimes things can't be factored. Like sometimes they are prime. So let's say I've got 2x squared plus 2x minus 5. Okay, this is not an a. It is not. So, I'm sorry, it is not a 1. So I'm going to have to do this Chinese method. The only way I can get a 2 is a 1 and a 2. So what are my choices here? I guess a 1 and a 5. This way I'll get 2. This way I'll get 5. So I'm trying to put them together and get a 2. A 2 and a 5 will never add or subtract and get me a 2. So now you think, okay, that was wrong. I'm just going to switch them. The 5 goes here and the 1 goes here. That has to work now because there's no other choices how to get a 2. Now I get a 10 and a 1. Well, a 10 and a 1 will never get me a 2. So this can't be factored. You would just say that it is prime. And that might happen. So on a test, don't think you'll always be able to break something down. Okay, so right now you would want to stop this video, and this is really the most important of everything that we've completed the most important types of factoring. So you'd want to go to your booklet now and do page 55. And then at the very end, right, there would be a page 56 and a page 57 summary where all these different types of factoring are thrown together. So I am really, this lesson can be over. You've learned all the important things, but I am going to show you one more little type of factoring that if you're really good with numbers and your recognition of special numbers is right there for you, you can recognize things, this will save you time. Okay, so there is something. So you can be done right now. You can go and do all that work in the book, in your workbook, but there is something called a perfect square trinomial. So if math is your thing and you want to know everything that you can figure out in terms of factoring, this is something that really is wonderful to recognize. So you're going to be given a trinomial. Something about this trinomial should strike you, okay? Where it comes from is, let's say I gave you this and I asked you to work this out. Remember what that 2 means. There's an x plus 5 and an x plus 5. So going through the multiplication and eventually putting everything together, you would get this. So this came from something very special. It came from the same binomial times itself, and it produced something very special. This is called a square value because I know its square root. The end of this trinomial is also a square value because I know its square root. And this 10 came from some very special numbers. It came from a 1 times a 5 times a 2. A 1 times a 5 times a 2. Okay, does that always happen? Well, how about if I gave you this and said, let's work that one out. You'd write it twice. You'd go through all your arrows in your factoring, and you have this trinomial. There's a square value, there's a square value. Where does 12 come from? A 2 times a 3 times a 2. So when you are given a trinomial and you're really observant and you look at this thing and you say, whoa, 4 and 9, those are square numbers. A 1, because remember there's a 1 here, a 1x squared, and a 25. Those are square numbers. Maybe I don't need to go through Chinese method and all this kind of work. Maybe I can do a quick little kind of shortcut. And the shortcut works by you recognizing these were square numbers, okay? So then you take the square root of this in your head. You should be able to see that's a 2. Times it by the square root of this, which is a 3, and then always times it by a 2. So a 2 times a 3 times a 2. If you get the middle number, it's very easy to factor this. So in this case I did, so now I need to know where did this come from. I've identified this as one of these perfect square trinomials where it came from something times itself. Think about it. If they have to be identical, what would have been here and what would have been here to give you 4x squared? There would have had to be a 2x at the start of each of them. And what had to end them if they were identical to give you a 9? They would have to be 3's. To end up with a positive 9, but by adding it a negative 12, they would both have to be minuses. So you take the square root of this, it must have started your binomial. You take the square root of this, it must have ended your binomial, and simply keep the sign that was there. And you'll have really quickly, instead of Chinese method and trying all this different stuff, you will have factored something very, very quickly. Okay, so one more. Let's say I have 16m squared plus 40mn plus 25. and I'm recognizing it's not going to be a nice easy one to factor, so I'm thinking maybe I have to go do this inspection method. Or quick look, especially when the numbers are big. Oh, those are square numbers. I'm going to do this quick little check in my head. I'm going to take the square root of this, which is 4, square root of this, which is 5, and I'm going to times them by 2. If you get the middle, this thing was a perfect square trinomial, and you are going to be done in seconds. So 4 times 5 times 2 is 40. So what much it must have started each one of these identical binomials to get this? It must have been a 4m. What must have ended each binomial to get a 25n squared? A 5n. If there's no minus signs there, then there were no minus signs here. Don't forget the 2, but you have very, very quickly worked that out. Now, had this been something else, had this been 16m squared plus 40mn plus 81n squared, okay, so this is the correct answer. You'd say, oh, I'm so observant here. This is a square number and this is a square number. I'm going to try that quick check. I'm going to go square root of 16, which is 4, square root of 81, which is 9, and I'm going to double it, and I get 72. Whoa, that's not the middle. So this is not a perfect square trinomial. It did not come from that. Okay, so you would try something else. You would now go with this Chinese method and do the crosses and try and factor it. And then if you couldn't, it would be prime. So there's lots of this neat practice on finding perfect square trinomials. It's you'll see it on page 54. So that's where you're going to see your difference of squares work. But in between here, they've also thrown in some of these perfect square trinomial questions. So as you're looking through those, your eyes should be on the first term and the last term and noticing that they have some special characteristics about them. Okay, so this is a long video, but I promise you getting through this will so be a benefit to you in Math 20 and 30. And as I say, if you're going to continue on with some math past that, this will make your life a lot easier. Okay, so work through some of this stuff. And like I say, the booklet is on Google Classroom there for you. Thanks for listening. Bye-bye.